Hi, everyone. My name is Goku, and I'm the founder of Made with ML, which is a platform where the community comes to learn how to combine machine learning with software engineering best practices towards building production-grade applications. And today I'm going to be talking about how to evaluate machine learning systems. And it's effectively become a medium where I distill a lot of things that I learned from industry and I share kind of in a first principles fundamentals kind of way with code so that other people around the world can kind of benefit from what I'm learning from and obviously have foster discussions so that I continue to learn more about these topics along with the community. But definitely today we're starting with evaluation, being a very data-centric topic in and of itself, and also how it impacts a lot of downstream processes as well. And there's so many nuances and dimensions to evaluation that I think a lot of people may not be aware of. And there's so many industry adoptions that I've seen just in the last year when it comes to evaluating machine learning systems. So today I want to kind of dive deeper besides, beyond the surface level of evaluation and talk about what I'm seeing in industry. And we'll actually go through the code to actually implement all of this as well. And then some of the more research side of evaluation that's actually very quickly becoming adopted into industry as we speak, but kind of draw that distinction and then definitely talk about all the different downstream data-centric aspects of evaluation as well. So just really quick about myself, before Made with ML, my background's in health and biology and worked on NLP for Apple for several years. Then went on to work in the oncology space, kind of combining machine learning with health data there. And then now I work with, predominantly on Made with ML, where I kind of teach everything that I've learned. But I continue to work with companies across various industries now and various maturity levels as well, which gives me kind of this rare opportunity to kind of see how all these different facets of machine learning development and production is done at different places, and then try to distill those fundamentals to share with the rest of the community. So, we're going to be focusing on evaluations today, but definitely check out the Made with ML platform where you can learn about all of this, and everything is 100% free and open source so that we can kind of talk about these things without any kind of barrier. This is kind of the rough agenda for today. Before evaluation, before we can actually talk about it, I need to kind of set up the scene. So I'll do that very quickly, a lot faster than we do in the course on the platform. And then definitely afterwards, I'll talk about the industry adoptions, the research trends, and then a lot of the downstream consumers of this evaluation report that we'll be generating. And the reason I wanted to talk about this topic today is, again, very, very data-centric. It's the central point where you need to be able to do evaluation to trust this probabilistic system that we're building nowadays. And then you need that evaluation to basically determine how something changes or how to change a process or do something downstream from deploying a model to monitoring it and definitely iterating on it. And the full course and all the code is on madewithml.com. I'm going to skip through the product and data side of things very quickly, cover that. But I am going to talk about, what is the actual task, how are we splitting the data, just because they're mandatory precursors so that we can actually trust the evaluation part of things. And then the downstream pieces I'll be talking about are around dashboarding, CI/CD, monitoring, testing, et cetera. But the focus will definitely be around evaluation itself. So in the actual course, we motivate, what's the scenario, why we're even using machine learning, which scenarios even mandate machine learning. So definitely check that out. But let's skip through a little bit and assume we're working on a case where we've already motivated machine learning. And the simplified task that I introduce here is that we have basically a data set of projects that has some text features like titles and descriptions. And then we have tags. So these are the labels. And you could be using this to, let's say, organize some incoming content on a website based on the labels, based on the tags here. It's a lot of different use cases, but this is the specific machine learning use case that we're trying to solve here. So the first kind of big task here is splitting the data. First, you want to make sure that the actual entire data set is representative of what we can expect in production. So, if we're trying to build a system that can identify inputs with these tags, we want to make sure our data set as a whole is actually representative. And then afterwards, each of the splits that we want to do to train our data, to validate, and then to eventually test our data, we want to make sure those splits are also representative of kind of the larger data set. So we want to make sure there's equal distributions of the different tags, et cetera, across the different splits. And depending on the specific task, you may want to shuffle or not shuffle your data. In this case here, we're absolutely going to shuffle our data. Perhaps some tags were more popular in the beginning, some later. We want to shuffle that so our models can learn how to kind of generalize across the tag space, the label space here. But maybe, if we're dealing with time series, we may not always want to shuffle our data. That can introduce things like data leaks. And once we have our splits, we can start to develop our models. And we have a whole lesson on how to kind of think about modeling and baselining. But let's assume we've kind of, start with some rule-based models. I'm going to skip through. We're not going to do rule-based things today. After you've motivated the need for complexity and the need for machine learning, let's say we have a model that's now outputting probabilities, and we apply some logic on those probabilities to say what the predictions are. So that's kind of what the baselining piece will look like. And obviously, there's a lot more we can do on, in the baselining. Traditionally, you'll fix the data and then work on, more and more complex models. But there's the flip side where you can fix the actual model and iterate on the data. And today, a lot of the things we're talking about in evaluation will actually touch on how we can actually iterate on the data. You can use evaluation to identify mistakes or augment data and figure out where your data is kind of less performant. You can use all those things to iterate on the data. So we've split the data. We have a baseline that's a machine learning model that does decently well. Now we want to actually assess what does this model look like when it's evaluated on a holdout, a separate test set. Evaluation itself has many dimensions. I'm going to focus on just the performance side today, but obviously you can evaluate things like the actual latency, the interpretability, the overall overhead, maintenance overhead. There's so many factors to evaluation. We're going to just focus on performance today. It's one of the key aspects and one of the more quantifiable aspects as well. But we have our model, we have our splits, we've trained our model. There are 3 artifacts that I need to do the evaluation piece. And that's true for everything that we're going to be talking about today. The first one is actually the ground truth. So what are the true labels that we can trust? What are the actual probabilities from this machine learning system that we've built? And then what are the predictions? And the distinction between the probabilities and the prediction is that you traditionally apply some logic on top of the probabilities. And this could be simple things like, if the threshold is below or above, let's say 0.5, you'll say it's this label or that label, but that can be fully customized, right? So we want to be able to know what that logic is to go from probabilities to predictions. But with these 3 artifacts, we can start to look at what does evaluation look like in industry right now, and then diving deeper from there. So something that everybody does that I talk to, which is great, because it's definitely kind of the bare minimum that we should be doing, is coarse-grained metrics, where we have some out-of-the-bag metrics like precision, recall, and F1 scores, which is basically just a weighted average of precision recall. We have these metrics that we want to be able to calculate, and we want to do that on our entire data set. So it's overall look, it's a very coarse look at evaluation for the entire test or holdout data set. And there's a lot of libraries. I'm using scikit-learn here to very quickly do this. You can also write your custom metrics and be able to do this. Now, the issue with coarse-grained metrics is that it's an overall look. And if you're, let's say in our scenario here, it's a categorical scenario, there could be some label, some tag that is less performant, but it's hiding because, all the other tags are performing well. So this overall look really doesn't tell me at a more fine-grained level. So some more teams, fewer than the coarse grain, obviously. But this is, I would say, also quite widely adopted in industry these days, a more fine-grained look. So, for us, we have these different tags. I want to know the performance for each of these different tags. So again, the same metrics, but on this specific subset, this time, based on the actual label. So here, if the tag is transformers, I want to know the performance for transformers. And this is a great way to just know what are these individual performances for these tags, and then be able to assess, is that because that tag doesn't have enough samples? Is that because that model is not able to pick up something for that, for the input space in that tag? There's a lot of exploration you can do with knowing this information. So it's really important to kind of have this fine-grained look. Now, kind of digging even further, we can actually create these confusion matrices, right? So we have these predictions and the ground truth. How many of them are true positives, false negatives? And traditionally, you see confusion matrix just plotted out. And while that's great for just kind of a high-level overview, you ideally want to actually look at the samples in each of those different quadrants. So true positives, while it's great that we're getting things right, it's kind of very useful to look at just to know that our models are actually doing well with this, given input space, and is able to map to the output space. Once you kind of look at that, you should really spend some time looking at the false positives. I would argue is probably the most interesting quadrant in the confusion matrix here, is because false positive effectively means our model has falsely predicted that this input belongs to this class. Now, while it's technically wrong, it's actually a great place to discover labeling issues. So here, the model could have actually learned quite a good amount of, kind of from the signal from the input space to know what the tag or label should be, but it's disagreeing with our ground truth. So perhaps the ground truth is wrong because there was something wrong with our labeling workflow. So this is a great kind of perspective in figuring out some mistakes in our ground truth. And then similarly with false negatives, we can look at these to discover, what about this input space is our model not able to capture, right? Because it's predicted a sample that doesn't belong to a class here. So we want to figure out why. And it's really great for identifying those kind of less performant areas of our data set. Again, all of this code to actually generate these confusion matrices is in the course on the website for free. But we're going to be looking at kind of the output so we can talk about all the topics that we want to hit on today. Okay, so now diving even further, so far we've used the probabilities, right, and then applied the logic to get the predictions. But what about just using the probabilities themselves? So this, there's a lot of different names for this. Popular one is confidence learning. What if I can use the numerical probability value to try to identify issues? So here, I may actually be getting things, the model may be outputting the right thing, but the actual underlying probabilities may be a little close to, perhaps the incorrect label or not as confident for the correct label as I'd like. So it's really important to kind of slice and look at this dimension as well. So some common things that people do are, the prediction is actually incorrect. You should absolutely look at the probabilities there and see what's going on. But what if the confidence score for the correct class is actually below some threshold? I want to make sure that when the model predicts something is a certain label, maybe I want to hit 80 or 90% every time. But if it doesn't, maybe there's something about that input or something about my label that's potentially throwing that off. And similarly for the incorrect class, you don't want to be above a certain threshold, et cetera. And you can also extend this to the continuous scenario as well, where you can look at kind of the percentage or deviance between the predicted value and the ground truth values. This is just a little code snippet here to show how easy it is to do this. And you can actually classify all of these into these different assertions that you have here and take a closer look. The issue is that today, with a lot of deep learning models, the assumption that we made is that the probability that the model outputs is actually, one-to-one in line with kind of the confidence, so the correctness likelihood. Now, this is largely true for a lot of models that are not so large and have a lot of different weights going through them. So if you look at here, Linnet from 1998, the average confidence is actually very close to the actual accuracy of the model. But on the same data set, ResNet in 2016, much, much larger model, you can see that the average confidence is significantly higher than the accuracy. And this is just the nature of kind of these larger models that we have today, where the models, and if you just look at the outputs, you can tell they're a lot more confident when they're predicting something. And it's actually not very reflective of actual confidence levels or correctness likelihoods here. So this is just something to be aware of when you are doing looking at the confidences here, or the probabilities. You want to be able to scale. There's a lot of different approaches. One of them is an extension of flat scaling. You want to be able to scale this so you can actually compare it to more realistic confidence levels. And one more topic around probabilities that I will touch on. This is kind of on the more research side of things, but it's very quickly, again, becoming adopted in the industry, thanks to libraries like CleanLab, open source packages, where you kind of insert your model, or you even use one of their out of the box models. You add your other artifacts, your probabilities, your ground truth, and basically look at the different probabilities and confidences to discover potentially mislabeled samples. So a lot of amazing work happening in this space for leveraging probabilities, so you don't have to do some of the more complicated calibration, et cetera, yourself, and definitely benefit from these packages. Okay, so those are the artifacts that we looked at to try to kind of look at, try to identify, starting from coarse-grained, getting into fine-grained, and then even looking at specific probabilities to identify errors or less performant areas. A different part evaluation is actually an extension of what we have already done. So if you go back to the fine-grained evaluation, we took each tag or each label And we basically said, what subset of data has this label, and give me the performance for that subset. We can actually repeat that same logic across many different axes here. So the concept is called slicing as a whole, but we can actually create manual slices across different things. So for example, we already did it for the labels, but you can also do it for, let's say, combinations of labels, especially if we're working in a multi-label scenario here. We can also do it for certain features. So let's say I want to know for this given feature, if it's this value or if it's between these values, just find the subset of data that has that value and give me the performance on that. You can also apply this to metadata, not features that are used by the model, but just features that are available in the data set itself, like timestamp or where the data is actually coming from, the source. And then obviously you can create your own slices. Like maybe you want to know performance on minority groups. So you want to know performance on your largest customers. These are slices that you can create. And obviously you can do this yourself with kind of native Python, but awesome packages like Snorkel would make it very easy. Just define the logic here. So here I'm trying to define the slice where I want to know all the projects that are computer vision and transformers, for example, right? So give me all the projects with both of these tags. And then I want to be able to define that slicing function and get the performance metrics just on that slice. So here I'm using an explicit scenario here where these are actual values. But I can also define my own logic where I want to say if the text, so title plus description, if the number of words is less than 7, then I want to create a slice called short text and get the performance just on that subset. So you can create as many slices as you want, whatever is kind of important to you, meaningful to you, so you can identify errors before actually putting things in production. But once you have these slices, you can get the metrics very easily by just applying on the data frames there. Now, the issue with manual slices is that you need to know what slices to actually create. So we're coming into the research side of things again here. But the concept of being able to generate slices so that we can discover the problematic areas in our data set prior to putting things into production. And this, if you think about it, you think of it like a search algorithm here, right? You have these different features and different values. How can we basically automatically slice based on these different dimensions and try to find meaningful slices that could be that will have poor performance? So there's a lot of packages, and there's research coming out every year on this, trying to basically combine concept of pruning, enumeration, and linear algebra to find these case slices of data that are going to be less performant than the overall performance on the entire data set. So very interesting line of work here. And this is great just to be able to have a data set and have all this evaluation happen for you automatically, and you can start to identify these issues long before putting things into production. Now, with generated slices, there's a few extensions I'll quickly kind of cover on. Obviously, the search algorithms, they work based on the features and the feature values themselves. But what if those values and things that we want to be slicing on are actually implicit? It's easier to kind of view this in an unstructured scenario. So here in images, these aren't explicit labels. But what if I want to create subsets of the data based on someone's hair color or gender or the background? And for text, if it has a contradiction or entailment, I want to create these slices on these implicit features and feature values. So a line of work that's happening here is that you want to be able to use clustering and other unsupervised techniques to first discover some of these implicit, they're called subclasses, and you can obviously have your own as well. So once you've discovered them, now you can isolate them and train models explicitly to focus on them. So you can basically train more robust models that are aware of these different subsets that you're asking to be focused on. There's an extension that takes us even further. So once you've learned what the subgroups are, can we learn networks? So in this scenario here, generative adversarial network that can map to go from one subgroup to the next. So now we're getting kind of data augmentation space where we can insert and remove a lot of these implicit features. Again, easier to view in the image scenario here, being able to put a label on something or a patch on an image or remove it and train models on this augmented data. So this is very much on the research side of things, but it's amazing that we're starting to think about data in this way, very much data-centric way, and understand all the things that can go wrong with our data set and actually now go back into the real world or augmentation world to generate data to make our models a lot more robust to these situations. Okay, so that's kind of a whirlwind tour of evaluation, what industry's doing, some of the more exciting research trends. what do we actually do with this? So let's say we have a report that's generated with starting from coarse grain to fine grain to slices, et cetera. We have a report of all these different values that we have. How is this actually used? So this becomes kind of the crux for a lot of the CI/CD workflows, a lot of the downstream workflows here. So the way we can actually use this report is to understand which criteria are the most important and which ones we can regress or absolutely cannot regress on. This is kind of pseudocode here, but it's actually realistic assertions here. Here, I'm saying the precision has to be better than the previous model's precision. There's no leeway here. The recall, however, doesn't have to increase, but it cannot regress more than 3%. Similarly, you can kind of incorporate different logic so that based on the report that's automatically generated on the new data set, model trained on the new version of the data set, you have the report. You can programmatically compare this report with the previous report and incorporate your own business logic to say something should be deployed, or rather something should be going to online evaluation plus experimentation, or something should be looked at because you didn't actually check off on all these different criteria. So it's a great way to programmatically use evaluation for iteration and downstream updates. Now, this lesson is on evaluation, but I'd be remiss if I didn't kind of mention testing because there's a lot of overlaps here. But the way I think about it is evaluation is definitely for a machine learning system. Even the artifacts that we used are, there's probabilistic components here. Testing, on the other hand, is kind of looking at the entire system as at a more holistic level where we don't necessarily care what the system is, whether it's deterministic or probabilistic. But I want to use the outputs to basically test the sanity of the system. So here, you can even have a rule-based system. I should still be able to apply these specific tests. So here, common tests that we have are, around invariance. In my scenario here, let's say I inject a verb. I want to make sure that doesn't actually change the outputs. In a different task, it may, right? But here, I want to make sure that it's invariant to these kinds of noise. There's also directional expectations where I know I want to make a certain change and it has to create a certain change in the prediction. And there's kind of minimum functionality tests where I want to be able to just check that certain combinations of basic inputs and outputs actually do occur. So you can, again, bake in these tests as well and have it be part of that report and use that. But these, should probably always pass just to make sure these sanity checks are never violated. And in the actual course, testing, there's so many different facets. There's testing your data, the model, the code itself. We definitely cover all of this in detail and implement it in code as well, but they all look quite different with a lot of overlapping principles as well. But definitely check that out on how to test the data, locally, but then in a more mature data stack, how teams are doing it these days, and then how to actually bake that into workflows so that it's happening on a repeated basis. So when you actually get a data and are building a machine learning system with it, all of that due diligence is already done for you, and you can just analyze the report if you want to. So now moving from, we have this report, things look great, all our criteria is passed. What's next? And a typical thing that you'll see is not actually production immediately, right? Going into production, updating the current system. It's this concept of online evaluation. There's a lot of different approaches here. Basically, we want to continue to try to do the same evaluation on our system, but now potentially on the new traffic that's coming in. And there's the approaches that we have here, common ones, popular ones, A/B testing, send some traffic to current system, some to the newer system and compare. There's canary tests where you can send most of the traffic to the current system, but just a small subset to the new system so you can see how things are going. And there's shadow tests where you can send all the traffic to the current system, but you send the exact same version to the new system, but any outputs of the new system are not used for anything. And you can compare this way. In the course, in the evaluation lesson, we compare the pros and cons for all of these in a lot more detail. Shadow may look like it's always the best, but there's a lot more about the system that's hidden here that may not always be the best choice. So definitely check that out to learn about the different approaches. But once we have this, another downstream aspect that's significantly impacted by evaluation is this notion of transparency via dashboards or documentation. You can effectively take a lot of the report and expose it, make it visible to a lot of the stakeholders. And this could be the product team, the management team, but it's really great to see improvement over time, or just see how we do on certain important slices, for example, and capture errors, et cetera. And oftentimes the best teams, I've actually seen this layer baked into labeling workflows. So when let's say false positives are discovered, it triggers the workflow, let's say a batch workflow that sends in these samples for a secondary inspection. And a lot of times this is where labeling issues are captured, workflows are altered after that. And it's just a great way to just identify issues and capture them before your customer reports it or some really important business metric suffers from that. And a huge part of evaluation is continuing to do it in production as well. That's where monitoring comes in. And yes, a lot of the components from our offline evaluation can be used in this scenario in monitoring, but there's some things to be aware of, like the actual window size, right? We don't, in our offline, we have this entire data set. We can create all these subsets and look at all these things. But in the real-time scenario here, once we have real data coming in, we can only look at windows of data, and it may not always have that distribution of across the different classes that we're looking at. So this can introduce a lot of things like false positives, et cetera. But it's really important to actually do monitoring. So in the monitoring lesson, I cover a lot more about how to identify, measure, and actually act on the drift. So definitely check that out. But you can see a lot of the ties with the evaluation, why it's important to have those offline components. So we continue to use them here. And just talking about slicing one more time, with monitoring in the online scenario, there are a couple issues, right? One, what if we need a label and that label isn't immediate, or there's some lag? The most popular scenario kind of approaches to that are, you don't have a label or it takes too much time. What are some proxy signals or approximate metrics we can use as kind of a secondary value? So if you have that and you have that kind of still meaningful signal, but not exactly label, you can use that to apply a lot of the offline criteria that you measurement criteria that you set up. If you don't have that, another approach, if you do have the labeling workflows kind of streamlined, is to sample a small subset of your daily or weekly production data, get that labeled quickly, and then create the same evaluation report for that newly fresh data that's labeled. If you don't have either of these things, a third approach that's again in the research side of things, but is very quickly becoming adopted, is the idea of using the slicing that we looked at before to try to approximate performance. So looking at this diagram here, they've created 3 different slices of data. This is in a text scenario here, and you apply those slices on the actual data set. And that creates a matrix, whether that slice is relevant or not relevant for that input. And with that matrix in our training data set, we have the matrix and the actual labels. Now with our production data set, we can apply the slices on the inputs because we have those, and you get this matrix. You can actually compare these 2 matrices to approximate what this performance would look like. And this works well for some scenarios, but the biggest kind of catch here is that you have to create the slicing functions that have good coverage on the data set. And by coverage, I mean you need to create the functions where you think drift will occur, right? So if it's a certain subset of the data set that you think will be the main source of drift, you need to have that as a slicing function. So that's kind of the big issue here. You need to have enough coverage, and perhaps as the generated slices space kind of improves, that this could be a very mature way to kind of approximate metrics. But just something I think everyone should be aware of. And the research on this is quite recent, but there's a lot happening every year as well. Okay, so that's kind of the holistic tour of evaluation for machine learning systems. You can see kind of how industry is maturing every year, and I kind of cover the same kind of view for all the topics in the MLOps course that we have. So definitely check that out. But yeah, it's exciting to see people kind of make evaluation the core point of their ML systems and use that to improve everything about the system. So I hope you enjoyed that, and definitely check out madewithml.com to learn more.